Now, we are going to discuss twisting of roving. The first question that comes to our mind, why do you need to twist the roving? To make it strong enough for winding on bobbin. A sliver, when it is stretched or drafted, it becomes finer by 10 times or 12 times. So, it is a parallel array of fibers, and this is very weak in nature, and this drafted sliver, which we call roving, is not strong enough to handle or to make it wound around a bobbin using mechanical means. So, we have to make this drafted product little stronger. And how do we make it stronger? The easiest way to make it stronger is by inserting some amount of twist, and hence twist is required in the roving. To make transportable package, so you have to make a bobbin, and this bobbin has to be transported from the roving frame to the ring spinning frame or ring spinning machine, and therefore, the package has to be strong enough to withstand the stress and strains of transportation, and therefore, a strong bobbin needs to be created where the fibers are really tightly bound into the structure. To enable an error free run-off behavior in ring frame creel. When we will discuss the ring spinning machine, we will see that when you remove the roving from the package that we make it here, at that time the roving should easily slide off from the surface of the roving bobbin. So, this runoff has to be very smooth and should not create too much of tension in the roving also, and that is also another purpose for which we have to make the roving little strong, so that the successive coils of roving, as you see how do you make a roving bobbin, the successive coils which are laid on the bobbin, they should not stick to each other. If they stick to each other, then as we unravel the roving from the bobbin, the roving layers will stick to each other, and that will create problem while unraveling, and hence the yarn also will be defective. So, from that point of view also we have to have a roving where it is little twisted, the roving has its own identity, and the neighboring rovings do not stick to each other. To consolidate in order to form a compact package. If we want to make a compact package, then the roving, if we do not have a twist, it is a fluffy mass of sliver, as you see it here. See, from here, if you look at this image or the photograph, from here, from there to here, this is the zone where we can see some twist is there, it is twisted part. Beyond that, actually it is within the drafting zone, it is a fluffy mass of material. So, if I do not have any twist, as the mass comes over here, it will also remain very fluffy. So, if we want to make a good package, a compact package, where the package content is sufficient, that whatever we need, then we have to first consolidate the roving itself, and for that also we have to put some twist, so that the roving diameter becomes less, and now they can be laid on the roving bobbin, and we can make a compact package. So, these are the reasons why we need to have some twist on the roving. Now, the question that comes, how much twist to be imparted? So, the very first purpose of twist is to give some strength to the roving. Twist should make the roving strong enough for winding it without stretch around the bobbin and without any rupture. So, while winding we have to ensure that neither it should get stretched nor it should rupture. So, it should have that minimum strength. However, the warning is that too much of twist means strong cohesive force between fibers, which will make it difficult to draft on ring frame subsequently. So, there is a danger also that if I have too much of twist, the roving becomes so strong, it will behave like a yarn and we will only be able to draft it on ring spinning. So, too much of twist is bad, too low twist is also bad. Again here one has to find out what is the optimum twist. The diagram on the right hand side shows how the strength of roving changes with twist factor. Twist factor represent twist, what it is exactly we will discuss in some other lecture, you will come to know what it is, but in a way it is defining the degree of twist which is present in a roving. And what we see it here that the roving strength rises very fast as we increase the twist factor, or if we say, we can also say as we increase the twist. So, we have to see that we should not insert too much of twist because it will make the roving too strong. The exact twist is a compromise therefore, between two conflicting demands to be able to produce compact package at high production speed and to be able to drop the roving on ring frame. So, one side requirement is I have to make a compact package, and if I want to make a compact package I have to make the roving diameter less and less. How do I make it less and less? I have to put more and more twist. So, that will satisfy the requirement of package content. On the contrary, if I put more twist, I will not be able to drop the roving on the next machine. So, the whole purpose of making a roving will be defeated if the roving becomes too strong. Now, this is a point that to be noted. Over the years, roving twist has been increasing because we are having high speed roving frame nowadays. Since we want to increase productivity, the speed of the machines are increasing, ring frame, roving frame, everything is increasing. And if we want to go for higher speed on roving frame itself, there will be more tension on the roving while the roving is being wound on the bobbin. So, there is a possibility of breakage during roving winding. So, how to avoid this breakage? You have to make the roving strong. So, over the years what is happening? Roving twist has been increasing because we are going for high speed roving frame. Since production rate we want to increase by avoiding breakages of roving, and package content also we want to increase by producing compact roving. And therefore, now the demand is on ring frame that the drafting system on ring frame should be capable to draft stronger roving. This was not there earlier, but this is what is required now. The modern drafting system of ring frame should have the capability to draft such strong roving. Consequence is to counter undrafted ends, roller pressure on ring frame drafting system had to be increased, because if we want to draft the strong roving, then we have to increase the roller pressure, and more pressure we have to put on the on the ring spring drafting system, and more pressure basically means more energy consumption also. But this is what is happening nowadays. Next comes twist, type of twist. That twist can be classified into two, true twist and false twist, and both the type of twist are present in in roving. But the true twist is present in the roving which goes into the bobbin, false twist part is present temporarily while the roving is being manufactured or is being made. So, we will discuss where do we have true twist and where do we have false twist. Now, true twist generation. Now, the diagram, one diagram that you see on the right hand side, what you see here, that there is a pair of rollers and let us say there is a strand like this as it is shown here, there is a bend in this strand and the strand is ultimately going on a bobbin. Now, let us imagine that this is the system we have and the bobbin is turning at a high speed. That means, what will happen? Rotation of the bobbin or spindle, whatever you assume it, because spindles, bobbins are mounted on spindles only. So, spindle rotation and bobbin rotation basically mean same. So, as the bobbin or spindle will rotate, it will cause the loop to rotate around the bobbin. So, this loop that we see it here, it will also rotate. As the loop rotates around the spindle, twist will develop in the loop, because one end is gripped at the delivery roller, at the bend it is turning. So, twist will develop between the bend and the delivery rollers, and now this accumulated twist will flow beyond the bend when sufficient twist actually develops in between these two zones, in this zone. So, every rotation of the loop will first generate one turn in this part of the strand, and with time more and more twist will be generated, twist will be increasing in this zone, and now the twist will be able to overcome the bend and will start flowing towards the bobbin. The actual dynamics of the twist generation is not being discussed here right now. At equilibrium, what will happen? The true twist that we will find in the roving can be found out from the ratio of rotational speed of the twisting element divided by the delivery roller speed. So, in this case the twisting element is the bobbin or the spindle. So, rotation of the spindle, that is, let us say in this case, in our case it is a plier. You will come to know gradually what is plier, or you can say spindle. So, that is Nf represented by the twisting element and delivery speed is V. So, Nf by V, this ratio will give you the equilibrium twist in the roving that we will find in the roving bobbin. That was the case of true twist. Now, let us see what is false twist. Now, in the false twist, you look at the diagram on the right hand side first. What we are showing it here, there is a pair of roller A, or you can say input roller, and there is output roller V, output roller, and V represents the velocity of the flow or velocity of the strand or roving, whatever you say, which is passing through this, that is what is V. Now, there is a twister, let us say, placed in between. So, we have a delivery roller from here which is feeding material, and the material is moving out from here. So, the nip here is A, the nip here is C, and B is the point where the twister exists. Now, let us first imagine that the roving or the yarn is not moving, but the twister is rotating. So, therefore, the roving or the yarn, whatever you say, is gripped in the nip point A and C, and it is not moving at all because V is 0, but the twister is rotating at a certain speed. So, what will happen as the twister rotates, twist will be inserted in the zone AB and also in the zone BC. But the direction of twist in AB will be Z as shown by this small lines, and the twist in the zone BC will be in the S direction. So, AB direction I will get twist in Z direction, and in BC direction I will get twist in S direction. Twist will increase in both AB and BC zones to their respective maximum value as the twister keeps on turning, and this is the situation that we will get. So, on the left hand side diagram basically means there is no movement of the yarn or the roving, whatever is there. Now, move to the right hand side. Now, let us say it is the same situation, but the yarn or the roving starts moving. So, V is greater than 0 now, it is no more stationary, it is moving. Now, what is going to happen? If the strand is made to flow, as a part of Z twisted AB portion reaches the BC portion where we have S twisted part, the opposing twist will cancel each other, leaving no twist in BC and thus in the delivered strand. So, the moment flow starts, that is the yarn or the roving starts moving forward, the twister keeps on rotating, we will always find that as Z twisted portion comes to the BC part, the whatever Z twist we had in that portion, it will be nullified by the twist which was present in the BC zone in the opposite directions, and the net result will be that the twist will be lost completely, and the fibers as they are delivered from BC zone will not have any twist. So, if we have a system like this, then the twist that you see in the AB zone, we call it is basically false twist, because this twist really does not reach the yarn or the roving finally, it is lost finally. So, if I created this kind of situation, then the final twist will not be there, but we will find temporary twist in the zone AB, and this situation is depicted in the lower diagram, how Z twist is going to increase and becoming reaching its maximum value here, and how the twist in the zone BC will change, that it will gradually increase and then start decreasing and becomes 0. So, this is how the situation will look like, and at equilibrium what we will find? No twist in the zone BC or the delivered yarn, but we will find twist in the zone AB which will be temporary in nature. This is what false twist is. Now, what is the advantage of this false twisting? By doing so, what do we achieve? There is a twisting and untwisting. As the yarn from this part will flow here, it will suddenly be untwisted in the opposite direction, it will receive opposing torque. By doing so, what we get? The part of the strand which is in AB zone, that gets strengthened. If that part is weak due to some reason and which may cause suppose breakage, then I can temporarily increase twist there and make it strong and avoid breakage. And you see the application of this in roving frame also. Now, roving twisting. The roving twisting will cause the drafted fleece to take a round shape. Here the diagram is shown. This is the fleece, this is the nip line of the roller, and then twist triangle gets formed in front of the nip line of the delivery rollers. Fibers, and the way the fiber gets twisted is depicted on the right hand side diagram. The red lines here is indicating typically as the fibers. So, when the fleece is being delivered, fibers are straight and parallel with respect to each other. And as if we want to know what happens to a particular individual fiber, that is being depicted by the red lines, and we see how these fibers is gradually changing its shape, because as it receives twist, it is made to follow a helical path. So, it is starts following a helical path gradually as it moves downward or it is flowing downwards. In the location 4, if you look at it, this is what the shape it will going to take. That is how the each and individual fiber will be following a spiral path. Tension and compression forces are generated along the axis of the fibers. Compressive forces leads to frictional forces which avoids fiber slippage. That is the purpose of basically twist, that by twisting we actually generate compressive force between the fibers. By twisting action we make the fibers to follow a helical or spiral path, and because of this geometry, whenever a tension is applied on such fibers, a transverse force or a compressive force will be generated, and due to this fibers will mutually hold or grip each other, or they will be coming into contact with each other, and due to this frictional resistance will be generated, and that will what will avoid slippage of fibers, and that is what is strength. Typical twist range is shown, like it generally varies from 15 to 70 turns per meter in roving. If we go by turns per inch, the value are 0.38 to 1.78 turns per inch. So, we actually give very low twist in the roving, because the drafting is still not over, we have not yet reached the yarn stage, and hence this twist is we only need it to actually make a package. Now comes twist insertion. So, how do you now finally insert twist? Twist is imparted by a flyer, which is basically a twister. In the previous slide we are saying twisted. So, twisting element in the case of roving frame is a flyer, which is shown in this diagram flyer. In the image also you find these flyers are there. So, flyers are mounted on a rotating spindle. So, there is a vertical spindle as shown here. The spindle gets its drive from the bottom, and on this spindle we mount the flyer. The spindles also can be rotated from the top or from the bottom, and because the flyer is attached to it, therefore, flyer becomes integral part of the spindle, and hence as the spindle turns, the flyer also will turn. Function of flyer is to impart twist, is twisting, and guiding the roving to the bobbin surface. That is another part, important function of the flyer. So, flyer what we see here in details, the construction of the flyer is shown here. It has inverted U shape. If you look at the shape, it is U shape, and there are two legs, one solid leg and one hollow leg. The hollow leg carries a pressure finger, which is shown here, pressure finger, or you call it pressure arm also. capable to swing at right angles on its lower end, as if it is fulcrumed over here in the lower end of the hollow leg, and it can actually swing towards the spindle and away from the spindle. That is how it is connected to the hollow leg. The pressure is balanced by a metal rod extending upwards along the hollow leg and pivoted about it just below the curve to the flyer top. So, here actually along this hollow leg there is a vertical rod, and the pressure arm is connected to the vertical rod also is a part of pressure. We will see what is the purpose of this pressure and what is the purpose of hollow leg. Hollow leg along with the pressure finger or pressure arm serves to guide the roving from the flyer entry point, that is the flyer top, to the bobbin. See, the roving has to now pass, it has to move from the, it enters the flyer top, then it has to ultimately reach the bobbin. The bobbin is also mounted on the spindle itself. So, the path of the roving is that it moves out from the drafting rollers, enters the roving flat top, and then it passes through the hollow leg. The lead has to be hollow, because if there is a hollow space there, the roving can easily pass through. The solid leg balances the hollow leg along with the pressure, because the hollow leg itself also carries the pressure, and therefore, right hand side has to be balanced by the right hand side, left hand side, and that is how the flyer is balanced. Therefore, this can be turned at a very high speed of 1000, 1400 or 1200 rpm. The hollow leg may have a slot sometimes starting at the top and extending down to the lower end. The slot helps to thread the roving inside the hollow leg in case it breaks. So, there used to be a slot. Nowadays, the slot may not be there in some flyer, but earlier there used to be some slots. The purpose of the slot was to basically push the roving so that we could easily thread the roving through the hollow leg. Nowadays, in many flyers the slot may not be there nowadays. The slot is curved to prevent roving passing through it to be thrown out during rotation. If you see the slot, you will find the slot is not perfectly straight along the hollow leg, it is slightly curved. The purpose of curving is that as the flyer rotates, the roving also rotates along with the flyer in the hollow leg. The roving also is subjected to centrifugal force, and the force may try to push the roving through the slot. If the slot is curved, then this possibility of the roving moving out from the slot will be much less. Otherwise, there could be possibility of the roving to actually move out of the slot, and hence this slot is actually curved. As I said, in some of the modern flyers, the slot may not be there at all, the hollow leg only exists, and we have a means to thread the roving through the hollow leg. Roving path, if you look at it now, roving is passed from the front roller nib, that is starts from here, front roller nib to the flyer top, it goes here, then it goes inside the top and moves out. So, it moves out like it is shown here in this diagram. It enters from the top, and then there is a hole through which it moves out. Thereafter, it takes a round outside. If you look at this diagram, that it moves out and then takes a round like this, it has taken a round here, and again enters, then only it enters the hollow leg. So, first it enters the flyer top, it goes downward a little bit, there is a hole through which it moves out. Sometimes it takes a wrap, the wrap can be adjusted, half wrap or full wrap or 1/4 wrap, and then it enters the hollow leg of the flyer. it moves downward and emerges out from the bottom of the hollow leg. After moving out from the hollow leg, what it does? It takes the support of the pressure finger or pressure arm for reaching the bobbin surface, because the hollow leg exit end is not really very close to the bobbin. Now, it has to travel a little distance from the exit end of the hollow leg to the bobbin surface, and there it is the pressure arm which gives it a guidance. So, as it is shown here, that as it is moves out of the hollow leg, the pressure arm is here or the pressure is here, and it takes wrap around it and then reach the bobbin surface. So, the pressure arm is basically guiding the roving on the surface of the bobbin. It is acting as a guide basically. It makes sure that the roving reaches the right place on the bobbin surface. Now, twisting process: as the flyer turns, twist is inserted. Twist originates in the region Q bar. Let us say this is the flyer top, this is the roving, this is the delivery rollers. So, first in this zone twist will be generated as the flyer rotates in the zone Q bar, and when sufficient twist accumulates here, it overcomes the resistance that is there at the point Q, but at the point Q there is a contact between the flyer and the roving, and in that contact there is certain amount of pressure because roving is under tension. So, this friction at the point Q will resist the flow of twist. So, when sufficient twist accumulates in Q bar, then only the twist can flow in the zone PQ. So, after the generation of sufficient twist, the twist can flow in the zone PQ. The flow of twist in the PQ depends upon the angle of wrap of the roving at the edge Q and the pressure at Q, which in turn depends upon the tension of the roving. Similarly, the twist will also flow from Q bar to RS. From RS it will go to the going to the roving. So, the first zone in the entire roving path where twist is generated is within the flyer top, that is the place Q bar as it was shown, and then it moves upstream towards the delivery roller, it also moves downstream towards the bobbin. That is how, but this everything is happening so fast that it is not really visible to us. The moment we switch on the machine, fraction of a second, this thing has happened. So, we will not really come to know that the accumulation process of twist in Q bar zone, twist then flowing in the towards the drafting rollers, these things will not be really visible or will not be able to really perceive it. And equilibrium twist again is the speed of flyer and the front load delivery ratio of these two. So, one thing there is little error here, this is the revolution per minute and front roller delivery is meters per minute. So, it will be Nf by V, and this is the typical formula that gives you the equilibrium twist that we get in the roving. Simple, the ratio of speed of the flyer divided by the delivery rate. The angle of approach, another important point here. As we all know that bobbins or the spindles are in two rows in front of the machine. Now, if we look at the roving path from delivery roller to the flyer top as it is shown in the diagram, The angle of approach alpha 1 and alpha 2 are shown, and you can see that they are really not same, they are different for the two rows of bobbins. And the length of unsupported part of the roving is L1 in one case and L2 in the other case. So, unsupported part is more for the front rows of roving and less for the back rows of roving. So, this difference is always there, and as a result what happens, the rolling condition around flat top are therefore not same and vulnerable to get stressed in an uncontrolled manner. That is the result which could be. The unsupported part is very long in this case, and we know the roving is most weak here. The roving is most weak from delivery roller to the flat top. This zone, the roving has no support from any other source, only some twist is there, and the roving becomes most weak in this zone. So, there is every possibility the roving might get stressed. Now, the roving twist is different in the two rows of bobbins, and the first twist generation we will see they will be different in this zone where the roving is unsupported. Counts are different also in two rows of bobbin because there is a possibility of some stretch of the roving. Roving is not really very strong, we keep very low twist, and roving is not very strong here, and there is every possibility that the roving might get stretched a bit in this zone, and if it is stretched by 10% or 5%, that basically means that the roving in one row will be 5% finer than the other row. And which row it is going to be stretched more? The front row of rovings are going to be stretched more than the back row, because the unsupported length is more here. Pressure arm or finger, it is shown here in the better way. We can see the way the yarn or the roving is wrapped around this. The function is to guide the roving from the exit end of the hollow leg to the bobbin. It was also told to you earlier. The other important thing, to adjust tension in the roving by adjusting wraps around it. This is very important to produce a hard and soft package. These points are important. See how compact roving bobbin we want to make, it depends upon at least two factors. One is what is the level of tension under which the roving is wound, and the other thing is what is the diameter of the roving. So, diameter is decided by the twist. Now, the tension under which the roving is wound, that is decided by quite a few factors. One of the important factor is the wrap around the pressure arm, other than the speed of the flyer or the speed of the bobbin with respect to the speed of the flyer. Those things also will matter, but very important as point is the wraps around it. If the wraps are less, the tension under which it will be wound on the roving will be less. If I suppose in case of A, the wrap is only maybe just one wrap. In the case of B, the wrap is more than one. So, in the case of B, we will be getting a roving bobbin which is quite hard, because the roving is going to be wound under a higher level of tension. So, this is the way by which we can easily adjust or regulate tension, and we can make as a hard package or a soft roving package. Now, we will come to first twist in more details now. Now, as I told you that the part of the roving which remains unsupported, that is from delivery roller to the flyer top, this part is very weak because twist is not much, and there is every possibility of undue stretch. Can I make the roving temporarily strong here and the answer is we can do it by having false twist in this zone, by generating false twist. So, by having false twist, it better integrates the fiber, it enhances strength of the roving, and as a result fewer breakage of roving, less friction while the roving passes through the flyer. Depending on the application, the following false twist inserters are available. We will see that in the next slide. So, here we can see here, this is the flyer top, this is the roving which is shown here. The roving is in contact with the top part of the flyer, and as the flyer rotates, the roving also gets abraded by the inner surface of the flyer top, and therefore, there is chance that it will create, it acts as a false twister. At the point Q, there is a bend, and here the roving will roll and it will generate false twist. The rubbing of the roving cross section against the edge of the flyer top leads to generation of false twist. Some false twisters are shown here. To generate additional false twisters are fixed on the flyer top. So, we have flyer false twisters available. These false twisters can be inserted or mounted on the top of the flyer. The very purpose is that it will generate false twist. Everything depends upon the intensity of the rubbing action, and therefore, we have false twisters of different design. In what way design varies? The design varies in terms of the number of grooves that is present in the false twister. So, these are the false twister. If you see carefully, there are grooves in it, and the grooves geometry can vary from false twister to false twister. There are numbers, their depth, and if they vary, they will have different degree of rubbing action on the roving, and therefore, different false twist will be generated. Now, in this case, if we will go by this, in one rotation of the flyer top, the number of rotation of the roving is expected to be the ratio of these two, pi d by pi dr, that is d by dr. Here is the roving diameter, and this is the inner diameter of the false twister. So, for every revolution of the false twister, we can expect false twist to be generated in the ratio of d by dr. So, false twist, if the speed of the flyer is nf, then I can have false twist to the extent of this much, nf into d by dr, with assuming 100% efficiency, which may not be true in many cases, because as the false twister, as the flyer top rotates, if you see the carefully, you will find the roving is jumping, is vibrating, and the roving vibrates. That basically means sometimes it is losing contact with the false twister. So, the efficiency of the false twister may not be 100% efficient, it may be little less, but the very purpose of false twister is to generate some amount of false twist in the unsupported part of the roving and make it temporarily strong, so that the roving does not break there. There are some more types of false twister being shown here. After this, we are coming to selection of twist. How much twist we should keep in the roving? As I said, the roving is not a yarn, hence high level of twist is not required, but too low twist is also bad, because that will make the roving too weak. But within this, the twist value that we keep, it depends upon the count of roving, it depends upon the raw material compositions, that is whether it is polyester cotton, polyester viscose. It also depends upon the length of fiber, it depends on the speed of the fire, and depends on the fiber quality. So, all these factors are important to decide the exact value of twist. The roving twist alone, however, is an imprecise measure for the strength of the roving. Roving count also plays a decisive role. So, strength of a roving does not only depends upon the twist, but also depends upon the count of the roving. Obviously, if the roving is coarser, strength will be more, because there are more fibers in the cross section of the roving. So, that also you have to take into account, and twist multiplier is a measure of twist that is independent of count. So, the concept of roving diameter and the count relationship we will now discuss. Ultimately, we are trying to control the roving diameter using twist. So, we must know what is the relationship that may exist. Diameter of roving, let us say, is dr, roving count is c in terms of text. The relationship between roving diameter and roving count in text can be stated by this simple equation. It is coming from the definition of count. We can write this. This is the definition of count in text is the weight of 1000 meter of roving. So, left hand side actually says shows the weight of 1000 meter, assuming the diameter of the roving to be dr. So, if we write this equation, then we keep simplifying it, we arrive at this. These are basically going step by step towards simplifications, and we arrive at the value of dr, which is this, where we see dr is a function of c and psi and rho f. These are the three quantities that we get, where c is the count, psi is the packing coefficient of the roving, how much fibers are packed, and rho f is the fiber density. The fiber density depends upon the fiber we choose, and these density values are available in the textbooks. Count, it is the count that we want to produce. So, C, but packing coefficient is something which is not really known or available, but it has been shown that the packing density or packing coefficient, whatever we say, varies between 0.1 to 0.2. This is the range in which it lies. A spun yarn will have a packing coefficient of 0.5, 0.6 in that range. Roving will have a packing coefficient of 0.1 to 0.2. So, if we replace psi by a value like 0.15, then we get a equation like this, dr equal to 2 under root rho bar c and by 47123.88 into rho f, and that can give us some idea about the roving diameters. And if we keep going further and further, then we can say that diameter of the roving is dependent on a constant k root over c by rho f, where the constant value is 9.21 into the power minus 3 in terms of centimeter if we want to find out the dr. Now, if rho f I replace it for cotton, then fiber density of cotton is 1.54 if we put, then I can write dr is going to be this value 7.42 into the power minus 2 root over c in terms of millimeter. So, dr becomes kc to root over c millimeter, where kc stands for constant for cotton. See, constant is 7.42 to the power minus 2. So, we can have a rough estimate of roving diameter from this equation. As I said, this is approximate value or a rough estimate. The roving diameter, otherwise also there are, roving is a very compressible material. So, the diameter determination of a roving is not really very so easy, but this gives you some kind of estimations. Other thing, the concept of twist factor will now also know in this connection. Now, let us say here is a roving which is shown, where there is one turn of twist is shown also. This orange line shows the helically lying fiber. The angle of inclination of the fiber with respect to the roving axis is alpha. Now, if we cut the roving and then open it out, and then we see, we will get this diagram as shown in the right hand side. Now, what is tan alpha in this case? The roving diameter is dr, that is, this is your dr, then this becomes pi dr, and this length is equivalent to one turn of twist, which is basically 1 upon t. So, tan alpha, this is alpha, this is also alpha. So, tan alpha is, if this is your alpha, so this is pi dr by 1 upon t, tan alpha. So, pi dr 1 upon t, that is basically pi drt. So, what is t? T is tan alpha by pi dr, that is tan alpha by pi, and what is dr? In the previous case we have seen, previous example, dr equal to k c root over c. So, we write it k root over c, or k c we can also write, and therefore, it becomes tan alpha by pi k root c. Now, this tan alpha by pi k, this part is written as T f, where T f basically means twist factor. So, twist T is twist factor by root c, whereas what is twist factor? Twist factor is actually tan alpha by pi k, that is what is twist factor. So, if it is tan alpha by pi k, then this becomes actually 1 upon pi k is another constant, which is, let us say, k 1, then it becomes k 1 tan alpha. Or if I, because twist factor is tan alpha by pi k, so we have written like this, or we can also get an estimate of twist factor. How? If I use this part of the equation, it is T equal to T f by root c, therefore, T f equal to T into root c. So, if I know the twist value and if I know the count value of the roving, I can find out what is the twist factor in it. So, we can determine easily what is twist in a roving, we can also determine what is the count of it, and if we know these two, we can find out what twist factor is in the roving. If I go to the other equation, this side, twist factor is tan alpha by pi k, and this is determination is difficult, because we need to know the alpha value. Measuring alpha is little difficult in comparison to measuring count or measuring twist. That is why, if we have to estimate the twist factor, we will always prefer T root c value. So, twist factor represents twist angle, that is k tan alpha in a way, which represents the severity of the twist without referring count of roving. That is what twist factor is all about. It is irrespective of the count of roving. With this, we close this particular session on twisting of roving. Thank you.